a small recap of what we did last time and what we plan to do today. We started our course on advanced compilers, and we went through the first lesson, which was very introductory and just raised a couple questions, and we picked a paper that we would like to dive into a bit more and potentially lead a discussion on it, maybe on some other stream. Anyway, if you're curious what is happening here, we are going through Advanced Compilers course by Cornell University. Which you can find here on this link. It's probably created by Adrian Sampson. And today we are going through the second lesson. We will watch the videos, and after that we will try to go through the tasks and complete them. I already prepared a bit and made demo available for me. It's a JavaScript runtime, and we can use a TypeScript compiler, so we are definitely can at least start doing something today, but I hope we will do most of the things. We're a little behind the schedule, but probably I still post a report on what we did in discussions, but maybe not, we'll see. The report is a part of the tasks. We will try to work in Pomodoros, not because it's some kind of special technique, but because I want to keep the breaks consistent, so I can talk, I can drink or walk a bit and refresh my mind before going further. You can write your messages in the IRC or chat, and maybe I will see them someday and will answer them during the breaks. Okay, I guess let's start.
Hi, and welcome to lesson 2 of 6120. Today I want to talk about how we represent programs for a compiler. What exactly do I mean by representing programs? Basically I mean what we consider to be the programming language when we are manipulating programs as part of the compilation process. So what we read in and transform and eventually translate into another language as part of a compiler. Of course, the most obvious way to represent programs is as text, that is as concrete syntax, the actual things that you type into a text editor when you're writing a program. So that looks like this for a JavaScript language, for example. It has lots of really nice properties. I'd like you to think for a second now about what are the strengths and weaknesses of representing programs as concrete text. Pause the video for a second, not for too long, to think about what's good about this representation and what's bad about this representation for representing in a compiler.
Let's go back a bit. The obvious plus that it's kind of human readable. the obvious downside that we need to parse this stuff to programmatically operate on it. Also, human readable doesn't mean that it's intuitive or consistent, and it's more a matter of particular syntax, but some syntaxes are better than others in some properties. I'm not sure if I want to talk at all during those pomodoros, but maybe sharing some thoughts from time to time is okay.
Obviously, this is a really easy representation to write. That's kind of the whole point, but it's a terrible representation for actually transforming. You don't really understand any of this is not the right level of abstraction for understanding the semantics of programs, which you really need to do in order to transform in, which is what we're going to do in all of 6120. So the next obvious step, the next obvious kind of program representation that you might imagine is abstract syntax. So instead of the concrete syntax of this program, it's easy to imagine a data structure that represents the same syntax, the same program, but in an abstract way. And that's an AST or an abstract syntax that you're doubtless aware of from any previous effort that you've, from any previous working with programming languages that you've done. If you've ever written an interpreter, you've probably used an AST. But just to give you an idea of what that looks like, the idea is that you have these, it's just a data structure that looks like a tree, where you have nodes in the tree that represent different parts of the program. So for example, we might have this top level notion of a program that contains, in this case, like a block of statements, and that has its own children for the 4 statements in this program that we just saw. Like for example, there's a let statement, a for statement, and this this like expression for the console.log. So these are all nodes in the tree. You notice that at this level we haven't like expanded out what goes into the let statement, but I will now fast forward and show you the rest of this tree. So I got a little bit tired of drawing the entire tree, but I think you can see what I'm getting at here. In this program, in this representation of the program, the tree is the tree represents like sort of every concept that you can have in the language as a node in this tree-like data structure. This by itself is already a vast improvement over the concrete syntax, and it's a lot easier to reason about what the program actually does, and it's not a bad representation for compilers. I'd like you to pause again, however, and think a little bit about the pros and cons of this representation. What makes this good for a compiler, and what makes this challenging for a compiler? Great ideas.
Okay, he was too fast. But let's think about this one a bit. Probably it's not enough information to do some kind of optimization so far. For now it's like very bare bone and doesn't have any semantics yet. And talking about pros, it's probably like quite simple representation of the program, and at least you already can manipulate it somehow. For example, expand macros or move nodes around or do something like this.
Personally speaking, I'd say that this representation, the AST representation, is perfect for writing an interpreter. It's really easy to see how to take a tree and use a recursive function to process the levels in the tree and recall yourself and to run the program. That is, like to process a block, for example, you just recursively need to interpret all the statements in the block while updating some reflection of the program's environment. It's perfect for doing that kind of a thing. In fact, it's really convenient for a lot of compilers. Plenty of compilers do all of their work on an AST representation of the program. It's not a terrible idea. In fact, I've written compilers myself that do exactly this kind of thing, that never really transition out of an AST that reflects kind of the structure of the original program. For this class, however, I want to show you a different approach, a different representation of programs that looks quite a bit different than the AST approach. That's going to be more convenient for writing a lot of interesting compiler optimizations. And that's to represent programs as lists of instructions. The main thing that this shift in representation is going to do is to make the representation more regular. That is, the one big downside that I see of the AST approach is that all the different types of nodes in this tree have different behavior. And if you want to write an analysis a compiler analysis that can process any program, you have to constantly be reasoning about the difference in semantics of all these different types of nodes. For example, this example has a let expression that has children that are the value to assign into, and the expression to evaluate on the right hand side to assign to put into that variable. So the thing about this is that the children mean very different things from each other, and they mean very different things still from, for example, this dot expression that I put over here, where the left-hand side is the thing is the name of the variable that we're accessing, and the right-hand side is the name of the field that we're going to be looking things up in. This goes on for the for statement and the assignment statements that we see throughout the rest of this program. All these different kinds of expressions, different kinds of syntax nodes have very different meaning of like what their children are relative to the node. So this is great for representing programs as humans write them, a sort of like intermediate level abstraction between the concrete syntax and something that a program can actually run. However, I think we can do better. That is, we can make things more regular and more predictable, specifically for the purpose of transforming in a compiler. So that's the next representation I want to consider, and it's the one that we'll be using throughout the rest of 6120, which is representing programs as lists of instructions. The idea in this technique is that you transform the program into something that looks like an assembly language. It's an idealized assembly language in the sense that it doesn't have like a fixed number of registers. It doesn't have like weird things like condition flags. It doesn't have all the other like horrible addressing modes that x86 has, for instance. But it looks like an assembly language in the sense that all it really consists of is a list of instructions, and those instructions have a very regular form. That is, there's just like a name of an operation, and there's a bunch of arguments to that operation. And they can sort of move values around from one variable to another. This is the kind of representation, for what it's worth, that underlies LLVM, and it's the same style of representation they'll be using in a programming language that I created just for 6120 that we'll be learning more about soon. This is an example of the same program that we've seen in the previous slide, represented as instructions in that simple language that we use in 6120. The idea is that there's in this version of the program, in order to represent things, there's not a bunch of different kinds of syntax nodes. There's actually only a few. You can declare functions like this. You can declare labels, which work just like assembly language labels, and then you can run instructions. So these instructions have an extremely simple and regular form. That is, they have a destination, here result. They have a type of that destination, and then they have an opcode saying like what to do, and then they have a list of operands. So this, for example, the ID operation is just the identity operation. So it does this very simple thing. It reads the value v1, does absolutely nothing to it, and puts the result into the variable called result. And it says that that thing has type int. This is a tremendously inconvenient way to write programs if you are human. You would never want to like write down programs in essentially assembly language structure, even if you get rid of the limits on the numbers of registers you can use, for example. This is a terrible, terrible way to write programs. However, it's a really, really convenient way to process programs as part of a compiler. I want to emphasize, however, that it is technically true that this instruction kind of representation of programs can also have concrete syntax and abstract syntax. It's just that the abstract syntax for instruction-based representations are super, super simple and extremely regular. So if we were to draw out the abstract syntax tree for this program using an instruction-based representation, it would just sort of look like this. There'd be sort of a top-level function node that takes the name of the function we're declaring, and then all of the children are just a very, very flat representation of all of the things in the body. That is, like, there's just a big list of instructions and labels. So the first thing in this program is a const instruction. So the const instruction has a few children. It has the variable we're assigning into. It has its type, and it has the value that we're going to put in there of that type. So that's 8. The second thing is an ID instruction. It too has a child that's the value we're assigning into. That's value here. It has the type of that thing, just like const. And then it has a list of arguments. Here, only one argument, and that's v0. Eventually, there are also labels in here, so there's going to be a label whose name is for cond, for example, and on and on. So the thing about this abstract syntax tree is it's very short and squat. It is technically an abstract syntax tree of a very different looking program, but the key is that this language is so much simpler and so much more regular that it's going to be really convenient for doing compiler analyses. Now would be a great time to pause and reflect on the advantages and disadvantages of this representation. That is, like, what do you like about representing things as like instruction-based languages, and what do you dislike about them? So,
let's think. First of all, it's a bit hard to reason about such programs because we don't have a notion of our usual things like functions. We have functions, but not in the sense of Lisp language when we have just nested expressions and the function returns only one value, and you can pass functions as arguments to other functions and all that stuff. We don't have a notion of records and all other objects of the language. Of course, it's hard to write such programs, but we won't be writing them anyway. It will be a job for a compiler to provide such a representation. It's a bit easier to transform such things because they much more regular than the syntax tree representation. We can find some patterns in the final result, like in this representation, and do those optimizations, which we almost can't do in abstract syntax tree, because like almost everything is very different. Of course we can do some optimizations on abstract syntax tree, but it will be much less repeating patterns in it, and it will be much more patterns here. And of course we need a slightly more machine operatable representation even of this language, because this one is text based and we still need to parse it to operate on it. It would be cool to store it in data structure, in some data structures that we can like really easily modify.
About them. So based on that instruction-based representation of programs, I want to talk about some of the ways that we extract better structure out of these programs for doing analyses. So rather than just treating things as one big flat list of instructions, there are obviously different ways to look at the program that will be useful in different scenarios for understanding different properties. The first one I want to talk to you about is a control flow graph. So the basic idea in a CFG is that every vertex is an instruction that is like something you might execute in the program, not a label. And edges between the instructions represent the transfer of control. So in this very, very tiny program written in this instruction-based language, there are only two instructions. There's one constant instruction and there's one print instruction. Super simple program. So by my definition of a CFG, there had better be two nodes. There is a const node that represents the first instruction, and there is a print node that represents the second, and the entire program for this one.
Okay, yeah, it's probably about cons of previous representation that we definitely have some instructions like jump, where you can arbitrarily jump between the labels, and it's really hard to operate on a thing where you can have arbitrary jumps inside the list of instructions. And what we basically do with control flow graph, as far as I understand, is we split our list of programs into the simplest list of operands which don't have any jumps, so they always executed like in sequence, and only after the last instruction we jump to a different place, possibly. So this way we will have our huge list of instructions with arbitrary jumps somewhere inside this list. We split it into a few small lists where all the instructions are executed sequentially, and this representation probably simplifies the reasoning about this program, and also allows to do some cool tricks like transforming those separate lists.
function called main can be represented as just a graph with an edge from this one to that one. That is that control, the program counter of the virtual machine that executes this program, will start with the constant instruction, and when that's done, it will transfer control across the edge here to the print instruction. Let's do a more complicated example. Not much more complicated, but here's a program that has a jump in it. The jump works exactly as you are familiar with in assembly. That is that this jump will transfer control to this label right here, and then start executing after that. Please draw now the control flow graph for this function. Great work.
He's so quick. Okay, I won't be drawing it. I don't have a pen.
My CFG that I drew, it has 4 instructions. That is, I didn't draw anywhere in here the label for somewhere. I just drew the 4 instructions that are normal instructions, that is not labels. Clearly we have just this, we have a const instruction that immediately after that executes a jump instruction. And the thing about that is that we know that the thing that will execute right after the jump instruction is the print instruction, so there's an edge representing that transfer of control. And we have one very lonely instruction hanging out all by its lonesome with no edges going in that is guaranteed never to be executed. And you can see that by the structure of the control flow graph. So it's actually worth noting now that this very simple alternate representation of programs, that is rather than just a big list of instructions, but as a control flow graph, has already led us to a really obvious conclusion. That is that there is some code in here that is totally useless and could be deleted. If we wanted to write our very first compiler pass on these programs, we could just construct a control flow graph and look for the lonely nodes that are guaranteed never to be executed and delete them, and that would be a form of dead code elimination.
Funny thing, I saw that in control flow graph you combine a few instructions that don't have intermediate jumps inside it into one node. But it turns out that every instruction represents a separate node in control flow graph, which is also okay, but not exactly what I expected and what I was talking about a few minutes before.
The important thing to emphasize, though, is by shifting the representation of the program, we were able to look at the semantics of the program differently, and different properties became obvious. Here's another program. It shows off a different aspect of the language we haven't seen before, which is that there are branch instructions. The semantics of the branch instruction is that you read a variable, and then you decide based on whether that variable, which is a Boolean, is true or false, whether to go here, to that label, or to this label. Please pause the video and draw the CFG for this program now.
We have one node, another node under it, and the third node, and after that 2 more nodes assignment and print. And also it's everything is okay. Yeah, it will be 1, 2, 3 nodes and 2 options to the left and to the right for assignment and print.
Or to this label. Please pause the video and draw the CFG for this program now. Here I've started drawing my CFG, and already I've run into an interesting issue, which is that when we draw branch instructions, it's important to, this is the first time we've seen 2 children of a given node, that is an out degree of greater than 1 for a node. For branch instructions, there is a difference between the 2 different destinations you can go. If you want to faithfully represent the semantics of the program, you have to distinguish between these 2. So it might even be helpful to, for example, label the true branch and the false branch. There's no need to label all the rest of the branches because all the rest of the edges, rather, because there's only 1 edge coming out of every given node. It indicates just sort of going to the next instruction. There's also 1 edge missing from this diagram so far. I haven't drawn the CFG edge that goes from this instruction after it executes. As in any other assembly language, it will proceed onto the next instruction, ignoring any labels, onto V. So I need an edge from after executing this instruction to executing this one. And then finally, we are done. In CFGs...
Oh, I forgot about this one. Because I, of course, thought about branching construction as if statement and didn't notice that they are sequential and there is no a jump after this instruction which goes out of the scope of print instruction. So yeah, my bad.
It's usually super useful to label the entry and exit to the CFG. That is where execution begins and ends. In this CFG, and in this language in general, the first instruction in the program is the first one to execute. So this is the entry instruction. we can label that in the CFG. And the exit instruction is the one at the very end of the function right before it returns. There's no explicit return statement here because this function doesn't return anything, but the last one that terminates execution of the function is the print statement, so we can label that too. The next evolution of these representations that I want to show you relies on the fact that this CFG representation I've been showing you so far feels a little bit redundant. That is, in particular, these chains of instructions that look like this are super, super common in normal programs. That is, it's really often that you'll draw the CFG with a whole bunch of blocks that are connected just one after the other with a chain of edges. And that's because that's how we normally write programs. That is, it often takes more than one instruction to run between interesting controls of transfers of control. That is, like, we need to do a few instructions, and then we need to jump to another series of a few instructions, and so on. So it feels kind of wasteful to be representing things as individual instructions when we can sort of think of them as one big block of instructions. And that's the concept of coarsening a control flow graph to use basic blocks. The intuitive definition of a basic block is that it is a chunk of instructions that all execute together. That is, if execution starts at the beginning of a basic block, it is going to finish executing at the end of the basic block. So it's one of those structures in the instruction-based control flow graph where you just sort of jump inevitably from one instruction to the next. We'll just gather those together and call those a control flow graph. To put it a little bit more crisply, a basic block is a sequence of instructions where jumps and branches. We'll just gather those together and call those a control flow graph. To put it a little bit more crisply, a basic block is a sequence of instructions where jumps and branches, that is transfers of control outside of just going to the next instruction, can only happen at the beginning and the end of a basic block. That is, you can't have a jump or a branch instruction anywhere in the middle of a basic block. It can only happen at the end. And any jump anywhere in the program, any branch, can only ever transfer control to the top of a different basic block. So to scroll back up to our longer example of an instruction, it's really easy to visually see the basic blocks in this example. This is a basic block because all the instructions come one after the other. That is, that there are no jumps anywhere in this range. However, we can't extend that basic block one step farther past this label because control will eventually transfer to that label called forecond. Because there is a jump that goes here, that must end the basic block. So that's a block. This is a block. And we have to stop it there because there's a branch instruction, and you're not allowed to keep growing a basic block beyond a branch instruction. Here's a basic block, and of course that has to end because there's a jump. And then finally there's a basic block down here. So it's really visually easy to see them in these programs because they're separated by the labels. And as long as you are jumping to that label, as long as you're jumping to a given label, that label must be the beginning of the basic block. Return to our definition. The nice thing about basic blocks from a compiler analysis perspective is that you can assume that if any instruction in a basic block executes, then all of the instructions must execute. And this comes up a lot when you're doing analyses. You don't really need to think about individual instructions. You can think about entire chunks of them and know that they all sort of execute together. So here's the same program we just drew a control flow graph a second ago at the instruction level. I would now like you to draw a control flow graph at the basic block level. Draw a CFG and label the entry and exit.
It will be 3 blocks, 1 with 3 instructions, and after it will be the second one and the third one, and like the same amount of arrows as we had before, like to the left block, to the right block, and from the right to the left.
Exit nodes, just as you did before, but this time do it for entire basic blocks. Here's my CFG. Did you get the same one? Great. One additional piece of terminology I want to layer on top here is that the set of instructions that end the formation of basic blocks has a special name. So for example, this branch instruction means that you can't continue making a larger basic block past this point if you imagine trying to grow your basic blocks as big as possible. These things are called terminators, entertainingly. So in this little language that we've been experimenting with, the only terminators that exist are the branch instruction and the jump instruction. So when you represent basic blocks in memory, you can think of them as just lists of instructions, where the last one is the only one that can be a terminator. All the rest of the instructions have to be non-terminator instructions. And of course, there are basic blocks in this program that don't have terminators, and that's because they fall through to the next instruction. So we've now seen 2 fundamentally different representations of these instruction-based programs. We can
focus.
Either think of them as just linear lists of instructions and labels, or you can think of them as control flow graphs, possibly at the granularity of basic blocks. We really need an algorithm to go from the linear list of instructions, which is how you might like store these programs on disk, for example, to extract a graph-based representation, to extract a CFG for doing interesting analyses. The first step is just to form the basic blocks. So we're not going to try to make a control flow graph yet. We'll do that in the next step. We're just going to try to take a linear list of instructions and chunk it up into blocks that we'll then analyze to make a CFG. So get out some paper, and we're going to together write the pseudocode for forming basic blocks. I like to write my pseudocode in kind of like Pythonish format, but you can do it however you like. But the way this is going to work is that you're going to start with a input list of instructions, and you're going to produce an output list called blocks. So this thing is just the flat list of instructions / labels that you've seen so far. So for example, this might contain like v0:int equals const 2. That's one instruction. And it might also contain like this great label statement, and so on. The blocks, that's going to be a list of instructions. So think now about how you would structure the search by walking over the list of instructions. Hilariously, I misspelled that. Call this insters. How would you loop over the list of instructions and create lists of instructions to put into this list of instructions that's going to be all the basic blocks in the program. Pause this video now and give it a shot. You don't need to completely work this out, but give it a try, and then we'll come back together and see if we got the same answer.
There's a small trick here. We can try to make blocks that include labels in themselves, because sometimes labels can exist, but nobody jumps to them, and in this way it's still a valid sequential block of instructions. For this one, I would take all the jump instructions first and see what the labels are used, and this way I can form the idea of block starts. In case we don't want to optimize the case where we have unused labels, we can just take all the labels that we have, and it will be the beginning of blocks. And of course the first one is also the beginning of the block, even without a label. To simplify it further, we can just put an arbitrary label at the beginning of the list of instructions and make the algorithm even more generic, like without edge cases. And after that, we just go through the list, we pick a label, we define it as the beginning of the block, and we keep adding instructions to this block until we reach a jump instruction. And after we found a jump instruction, we can say that now we need to create a new block, and the next thing after the jump instruction will be the beginning of the block. And we keep adding instructions until we reach either label or a jump instruction. If we see a label, we create a new block and keep adding instruction, like start adding instruction to a new block. If we see the jump instruction, we understand that it is the end of the block, and we create a new block and start adding instructions to the new block.
But give it a try, and then we'll come back together and see if we got the same answer. So here's what I would do. Because I like to write my pseudocode in like fake Python, I would start out with a for loop that says that like for I in insters. So the way this is going to work out is I'm going to walk over every single instruction in sequence and hope that I can glue together blocks on the fly. As a kind of supporting.
Actually, we don't need to add a label at the beginning of the list, because we can already say that the first block starts at the point of time before we start a loop, and when we start iterating through the instructions, we're already adding all instructions to the first block.
Data structure, I'm going to need a list for the current block that I'm currently forming. So the block starts out empty, and then we're going to fill this up, and then empty it out, and then fill it back up again, and then empty it out, every time adding it onto the list of blocks. Inside the loop, the main thing that I need to do is check whether the instruction is something that should end the basic block. So if it's just a normal instruction, we'll put it on the block, and if otherwise, we will end the basic block. So the things that matter here is if I is a label, that means we have to end the basic block because a jump might be incoming to the next instruction, or it's a terminator, that is branch or jump. If so, then we need to end this basic block.
The difference between label and terminator is that we don't add a label to the block, but we add a terminator to the block. And what I would do, if I meet a label, I push the current block to the list of blocks and I reset the block to empty list and proceed further. And if I see terminator, the further stuff will be just adding instruction to the block, and the next step will be checking if the current instruction is terminator, and if so, we push the block to the list of blocks and reset the list of instructions in the block again and reiterate.
So here's a pseudocode for that. Again, in Python style, I will say that we will empty out the block, but before we do that, we'll put onto the end of our output list of blocks the current thing that we have built up in the as our current basic block. Of course, this algorithm isn't that great yet because it doesn't actually put anything to any of the.
Is it wrong? If our instruction is a jump or branch operation, we need to add this instruction to the block first before saving this block.
Blocks. It's just going to append a bunch of empty blocks to the output. What we also need to do is actually put these instructions into the blocks. The way I'm going to do that is that whenever we see an instruction, as long as that thing is not a label, we'll put it into the current basic block before terminating it. So I'll just say in Python style, block.append I. So that way it works is that everything, including terminators, is going to go at the end of the currently being formed block, and that also, if it was a terminator, or if we saw a label, then we'll end that block there and start a new one afresh. So that's the algorithm for forming basic blocks. I hope you got the same thing as I did. The next thing that we're going to do is
this way our blocks won't contain labels. However, they should be somehow connected. The labels should be somehow connected to the block, so we can later understand, how to build graph from one block to another. So somewhere here we need to store this information. Either we need to add a label as the first instruction of the block, or we need to attach some meta information to each block somehow.
Use that list of blocks to form a control flow graph. To do this, we will, I'll just give you a hint, we're going to need an additional data structure that we didn't do when we were forming basic blocks, which is to map from labels to basic blocks. That is, we're going to know which labels mark the beginning of which basic blocks. So going back to one of these example programs, we sort of want to associate this label with this block that follows it. You can sort of think of it almost as like the name, the identifier of that block is here, so that we know that anywhere in the program where we jump to the label here, we know that we, in the control flow graph, need to think of an edge going to the here block. So you can imagine that we've done that in the basic block formation process. That's really easy to do.
But if we have a program which contains jump instruction, few usual instructions, jump instructions, few usual instructions, jump instruction, it will be few unnamed blocks, and we won't be able to associate no name for this block. For every label we have only one block. It's probably true, because actually we can, in this representation, we can do the following thing. We can put two labels on two consequent lines, and this means that both labels will be referring to the same block, but it's not a problem, because our data structure maps from label to the block, not the other way around. But for many blocks it won't be any label. But okay, I think he wants to associate only labels with blocks, but it doesn't matter if every block has a label associated with it.
All we need to do is come up with another like label to block data structure. This can just be a dictionary, and the way that it will look is it will map label names, which are just strings, to these like lists of instructions. I'm sure you can see how to modify the basic block formation process to also keep track of the labels that are associated with each block, and then in the next step we will use those to form the control flow graph. So in the CFG formation step, we're going to start with those inputs that we just computed in the basic block formation step, and we're going to compute exactly one output, a variable we can just call CFG, which we're going to make a dictionary. And this is going to be a representation of the graph, just using an edge list format. So this CFG dictionary is going to map labels, which remember are just strings identified as basic blocks, to a list of all the labels of the successor blocks. A string and exactly one. Start with those inputs that we just computed in the basic block formation step, and we're going to compute exactly one output, a variable we can just call CFG, which we're going to make a dictionary. And this is going to be a representation of the graph, just using an edge list format. So the CFG dictionary is going to map labels, which remember are just strings identified as basic blocks, to a list of all the labels of the successor blocks.
But what about the named blocks? The blocks that don't have any labels.
Successors are CFG terminology for just the nodes on the other end of the out edges from the current block. So if this is us, if this is some block that we're processing, then the things that have edges into this, all of these blocks are called predecessors, and all of these blocks that have out edges from the current block, those are called successors. So this CFG thing, again, is going to map blocks to a list of all the successors of that block, and that will serve as a representation of the CFG. So imagine you have already formed the basic blocks, and now it's time to write the pseudocode for forming the CFG. So please pause the video and give it your best shot. Again, you don't need to completely finish this, but give it a try and see what you come up with an appropriate level of detail, and we'll come back together and compare our answers. Here's my rough sketch of the algorithm. It's going to start just like it did with the basic block formation thing, which is that we're going to start with a for loop that loops over all the stuff. In this case, we will look at all of the blocks in this list of blocks that we computed in the previous step. The strategy I'm going to use on every block is to look at its last instruction. That is, look at the thing that might be a terminator or might be just nothing if we're going to follow through. So we'll get that last instruction, call it last. This is just an instruction. And in Python terms, the last thing in the list, that's block -1. Okay, I'll use that. So I'm going to divide into 3 cases. The instruction might be actually, let's do jump first. So if it's a jump instruction, the jump instructions only have one destination. That is, there's only one successor of this block. So the thing we'll need to do is just add an edge to the graph that goes from the current block that we're processing to the destination of that jump.
It's very cool. But how you add the edge from block if the block don't have a name, don't have a label before it?
I'm glossing over a little bit here because I'm not managing the distinction between blocks and the labels they're associated with, but I hope you can forgive me that we can just sort of merge those two things together in a real implementation. The next case that we will need to worry about, other than jumps, is that it is a branch instruction. And branch instructions, of course, are just like jumps, except they have 2 different destinations. So we're going to need to add 2 edges to our graph. I used last.true and last.false here to mean the 2 different destination labels of the instruction. That's just sort of like made up syntax for how you might traverse the actual AST for these programs. But I hope you are assured that it's not going to be that hard, regardless of whatever data structure you choose to represent instructions. There's one final case. That's an else if. This is the else case. We're going to have to deal with cases where the block doesn't have a terminator, that it doesn't end in a branch, so it's going to fall through to the next block. We're going to need to add an edge to the graph for that as well. I'll just say add edge to block +1. That's, again, a total abusive notation just to say the next block in the list. In real Python, of course, you need to sort of keep track of where you are in the list and look at the next thing. And also add a qualifier on here to say if it exists. That is, if this is the last block and the next thing is just the closing curly brace for the entire function, then we are done and this is the exit node and we don't add an edge to the graph. So that's the algorithm for forming a control flow graph. And this sort of shift in representation is the first of many that we'll do in this class to look at programs differently so that different properties become obvious when we're doing analyses.
It's fine, the question is still open, but okay, I think it doesn't matter too much, at least at the moment.
In this video, we're going to get our hands dirty with manipulating programs written in the programming language that we saw at a very high level used in the previous video, the one with all the instructions. That one we were just sort of using as a fuzzy example of a notional programming language. This time we're going to make it concrete with real code. So the code that I was showing you previously maybe looked unfamiliar because it's a programming language that I invented just for 6120. The programming language is called Bril, for the Big Red Intermediate Language. And it's what we're going to use for the first few months of this course to sort of get familiar with manipulating programs without going full scale on and interacting with real world programming languages like C or using real compiler infrastructures like LLVM. This sort of provides a nice way that is indicative of how real world compilers work and presenting quite a bit of their complexity while sort of sweeping under the carpet a bunch of the rough edges that make it hard to get started. The idea behind Bril is that it's a very, very simple and extremely regular intermediate language that's based on instructions that you can extend as much as you want to make it as interesting as you want. So it's not just a fixed language, you can add whatever extensions you want on top of it. So we'll start by playing around with the very core of the language, but there are existing extensions that make it more interesting, and you can, of course, add your own. The canonical home for everything related to Bril, which is the Big Red Intermediate Language, is here at this URL that you can find linked several places from the 6120 website. You'll also want to check out the GitHub repository that contains a kind of monorepository with a bunch of infrastructure and the documentation related to Bril. So a monorepository means that there's a bunch of different tools in here, and they're all interrelated, even though they're kind of separate tools. But we're going to start out with just sort of getting a feel for what this language is like. Let's get started by looking at a very simple example of a Bril program. One of the most important things about Bril is that the canonical representation is as a JSON document. JSON is just a serialization format. It's not all that interesting, but the point is that every single language out there has a built-in library, for the most part, for parsing and emitting JSON files. So there is no canonical language that you need to use to process Bril programs. You don't need to write a parser. Remember, this class is definitively not about parsers. You just need to use a built-in JSON library in order to start processing Bril documents. You don't need to use any existing infrastructure. So the way that a Bril program works is that it starts out, the top level in a Bril program is just this dictionary that says, here are the functions that it contains, and then here is a dictionary that contains a definition of a single function. You'll see that there's a sort of a key value structure going on here. We have the name of the function. It has no arguments, but there is a list of instructions. So the instructions contain the body of the function, and each instruction in the body is just a JSON dictionary. So this one has exactly 4 instructions. There's a constant instruction indicated by its op being const. There's a second one, and then there is an add instruction, and then finally a print instruction. These correspond to the much more readable and more human writable text format that we saw in the document in the previous video. I'll show you that one, that text equivalent now. Here's the text equivalent of that same program. And I really want to emphasize that even though this is way more convenient for reading and writing, it is not the canonical representation of the Bril program. The text format is just an alternative representation that is fit for human foibles. The actual representation, the canonical one, is for computers, and that's the JSON representation. But you can see that there's a one-to-one correspondence going on here. The @ symbol means that we're declaring a function, and then there are 4 instructions in the body. There's 2 constants, that add instruction, and finally the print instruction. It's very convenient to be able to read and write programs in this format, but then to do anything interesting with them, we will translate them into the JSON representation and then do stuff from there. Load them up in whatever tool you like, transform it, and then emit it back as JSON. I have provided for you already a parser and emitter for this text format, which means that you never have to touch a parser in the entirety of 6120 in order to use Bril and to write interesting compilers. You just have to process the JSON representation. Next, we're going to get the Bril tool set up and start processing some programs. The first thing to do is to clone the repository. Then the next thing we're going to want to do is install a couple of the tools. In the documentation, you can see there's a bunch of interesting tools that come with Bril, but a couple of them are more important than the others. In particular, the things we're going to want to use the most are the implementation of the text representation, that is the parser and emitter that go back and forth between JSON and the human readable form, and the interpreter, that is the thing that can actually execute the programs and tell you what they do. Super important. There are documentation about how to set up each of the tools in here, but there's also, for those 2 most important tools, you can also see setup instructions in the README. It's not hard at all. The first thing is in the Bril TS directory. That includes the interpreter, also a language definition in type.
I already packaged Dino runtime to be able to use Bril TS. Boom, boom. And I already copied the repository for the Bril language. And we have this to Bril file, and we can compile it with Dena. I already tried to compile it today, and it created a binary here in .dino bin ts Bril. Oh, okay. It just wraps it into script. And if I set the path variable, now I can use test to Bril.
TypeScript if you want to use TypeScript to manipulate Bril programs, and then it also contains a very, very limited compiler from TypeScript into Bril, which makes it easier to write longer programs. But the thing you need to do in here is you'll need the yarn package manager. You can also use npm if you know how to do that. In any case, you type yarn to install all the dependencies, yarn build to compile the TypeScript code, and then you can type yarn link. This adds to your path a program called Bril for the Bril interpreter. This is something you can pipe Bril programs into in their JSON representation in order to run them. For example, there is a program in the
where is Bril interpreter? Time for a short break. Okay. Sorry.
test directory. Here's the add program we just saw before. If you pipe that into the Bril interpreter, it will run the program, and when it hits a print statement, it prints out the result. You notice that I used a less than.
Okay, we are looking for Bril interpreter, but there is no interpreter here. Bril.ts. Ah, okay, I see. Bril.ts. Okay. And now, so basically, as I understand, then is JavaScript, TypeScript, WebAssembly runtime. So it can run TypeScript directly, and this command just creates a wrapper for this Bril.ts file, which just runs Dino with specified file and like accepting all command line arguments. That's basically it. That means that we can do the same trick as he did. Enter P. What he did? Test print at JSON. Okay, my bad. It expects the program to be on Mastodon, so it was waiting for the input. Do I want to write Geeks package definitions for this course? So the only thing you need is actually a Geeks, and the rest can be obtained, compared to your environment, like easily. Sorry. I have probably added to something. Okay, it can work with only JSON representation. Let's see. Bril or camel. Okay, it seems it's interpreter written in a camel. Or not interpreter, it may be thing that translates from Bril to JSON and vice versa. I'm just curious. Okay.
In that previous command, that is to indicate that we're reading from the file and piping that into the interpreter. Next, we'll want to set up the tools for the text format. So there's a directory called Bril text here. This thing is written in Python. So we've already seen two different programming languages interacting with Bril programs. And again, this is part of the philosophy that you should be able to use any programming language and any set of tools you like in order to load up and manipulate and interpret Bril programs. These ones are in Python, the previous ones are in TypeScript. For this, you'll need a tool, a package management tool for Python called Flit, which you can install in kind of the obvious way. Then you'll have a tool called Flit, which you can use then. Say flit install, and then there's many different options for the flit install command, but the ones that I recommend are symlink, so that you can make changes to the text format if you want to, and then, or like pull updated changes in this Git repository, and they'll get reflected automatically, and then user just to install it without super user permissions. Then you will have tools, aside from the Bril interpreter, you'll now have two different tools called Bril to text. That takes JSON documentation, JSON representation of Bril programs and dumps them out as human readable text, and the Bril to JSON, which is a parser that emits the JSON representation. I'll show you how to use those two things now. We can do Bril to text on the program we were just using before.
The amount of package managers for different languages I see is like horrible. I never heard about Flit. I don't see how it's reproducible so far. Doesn't matter, at least for now.
So under test, add.json, that takes the JSON representation and dumps it out in the text format we just saw. The Bril to JSON thing does exactly the opposite. So in fact, we could take this thing that is currently a human readable representation and pipe this into Bril to JSON, and that should print out the JSON representation. The nice thing about this then is that you can take this JSON representation and pipe it into the Bril interpreter if you want to actually run it. So using these Unix command line shells, you can build up more and more interesting pipelines. For example, if you write an optimization or a transformation on these things, you can just put this in between the thing that emits JSON and the thing that runs the programs in the pipeline. So like my great transformation, if you wrote that thing and that was a command that was available, you could transform programs before feeding them into the interpreter. Your task for lesson 2 is to load up Bril programs and write some code that does something to them. It doesn't have to be that interesting. In fact, it should be somewhat unambitious. It's just to get you sort of familiar with the Bril ecosystem and to understand what it's like to process these programs. In the rest of this video, we're going to do some of that together. I'm going to get started, at least, drawing the control flow graph for Bril programs. That is forming basic blocks, just like we did in the previous video. You are welcome to follow along. In fact, I encourage you to follow along. You don't have to follow the code exactly.
Okay. Let's take a look. In this makefile. Seems good. And now we need a channel slog that I will take from Actually, let's rename it to env. It will be I can't type. Sorry. It will be don't need this stuff. Actually, I can just do Guile. Don't even need this stuff. And this one. So that's basically it. To be sure that we're using the latest stuff, that IRC Guile. I'll do this trick. I'm just making sure that I use like very latest version of Guile IRS, not the one published in RD repo. Hello everyone. Hello. I'm very quiet. I was saying something out loud or mumbling, whispering. Bless you. The sneeze was loud, by the way. Thank you. How is this course any good? Yep, it's good so far. There's only like a problem with it, like a minor problem. It has a lot of different tools like JavaScript runtime, Python package manager, and all that things, and I tried to make them available. And I already succeeded to build a few TypeScript applications and the runtime from the release binary. And basically right now I'm setting up the environment for Guile so I can do some basic stuff with it. And to actually perform some exercises. But it takes surprisingly a lot of time. Okay, while we are waiting the build, we can keep watching.
Exactly how I do it. You can, again, use any language you want. I'm going to do this in Python just because it makes it really easy to write like pseudocode-like processing algorithms, but you can use any tool you like. And if you do this CFG exercise, I think you'll learn a lot. And if you think up one additional thing that you can do on top of this and turn that in for your task for this week, then you'll be up and running with the Bril ecosystem. Anyway, to get started, I'm just going to start completely from scratch and make a CFG extractor in Python. Let's do the normal boilerplate. I'm just going to have a function called myCFG, I guess, for now. And I know I'm going to need Python's JSON library in order to load up programs. I'm also going to read them from the standard input, so I'll need sys. Okay, we're almost there. We've almost loaded a Bril program. All I need to do now is just json.load sys.stdin, and now I have a program. Just to make sure I'm doing everything right, I'm just going to print that out. So we need an interesting program. There's a whole bunch of them in the test directory that come with the Bril repository. So for example, under test, and the interpreter test has lots of things, like there's a jump test, for example. Let's take a look at that one. This is a great program. It contains one jump. In case it should make for a like semi-interesting control flow graph. To use this, of course, we can't pipe this directly into our program because it's not in the JSON format. So what we'll need to do is run that Bril to JSON program and pipe in this jump program that we were using. And now we'll pipe that into the myCFG program. And then unsurprisingly, it just prints out the Python representation of that JSON. Great, cool. Okay, we're pretty much good. So these programs can have multiple functions. For this purpose, that doesn't really matter. So I'm just going to loop over the functions.
So I basically want to repeat the same stuff. Trying to come up with a good model name. Core SM. Make directory and define model 6120 core like this. And we need to use models JSON, I guess. Use model. Cool. Go to model JSON. Re-export models. I need JSON parser, right? JSON to SCM. We need JSON to SCM, which takes port. Okay, let's first do a small trick with input from file. One small thing. and we are finished, and we'll take a break. I want some Bril test print at JSON. I want this file, and voila, we have the Bril language loaded into our scheme file. Very nice. A small break. I don't answer questions usually during the stream, but during the 25 minutes of work, because I don't want to switch my attention, and I answer questions during the breaks. So if you have any questions, it's a good time to ask them. I will left you for a couple of minutes, but I guess I will still be able to answer the questions you have. Oops. I will keep microphone out of my mouth for a while to eat a carrot and not disturb you too much. But the idea I got during the time in bathroom is the following: is to package all the tools needed for Bril into Geeks environment, so it can be instantiated with Geeks shell or accessed with Geeks API to build, you know, all the fancy stuff.
In the program, and then do something with them. I guess the first thing I'm going to need to do is form the blocks, form the basic blocks. So I'm going to make a new function called form blocks, and I guess all it really needs is the insters from that. Let's call that the body of the function. I know I'm going to have to do something that like loops over the instructions in the body, but just to make sure that I'm doing this right. That's not right. Cool, so those are the instructions in the body. Now we're going to
It will be index and vector element. Let's just print it, and now we need to get sock ref, not very helpful, doc string, a list and key. Okay, our a list is Bril program, and key will be functions. It's string. Okay, string like this, and with a vector for each defined. It's very funny that we have a function that returns a vector, but we don't have vectors to operate on it. What is this thing that appears from time to time? Use model JSON survey 43. Format true with backslash. Okay. What we have here? Define print no, function in block instructions, yes, no, probably no. Function instructions, fun, a sock ref fun, insters, like this. And it will be instructions very cool. And now define print instructions vector for each lambda ex format true \n print instructions. Boom. Looks good.
Actually do our algorithm for forming the basic blocks. So as I recall from my algorithm, we had this thing called block, which here I'll name a cur block. That's going to start out empty, and we're going to loop over all of the blocks. And I guess I will use Python generators to yield the current block as I build it up. But I guess the point is that I need to terminate the block if I encounter a label or a terminator instruction. And otherwise, I need to add things to the current block. I think we got that right. Okay, so anyway, but I will... I guess the top level thing I need to do is distinguish between normal instructions, like actual instructions, and labels that appear in this list. That is, like, we have some maps that have a label thing in them, and then all instructions will have this like op field in the dictionary. So I can distinguish between actual instructions and labels by doing this. And we'll do something here.
Okay.
So this might be a label. Anyway, I have to do one thing in the case that it's an actual instruction, and another thing in case it's a label. So the way that it worked, I think, from our pseudocode is that if it's an actual instruction, then regardless of what it is, regardless of whether it's a terminator or not, we will want to take our current block and append the instruction. So this is going to become a list of instructions, including the terminator for this block. And the point is that we now need to check for a terminator. And we're going to do that is say,
I need somehow to make Bril to JSON work. So now I will go through the repo and we'll see if there is TypeScript version of Bril to JSON, or I need to deal with Python to actually have this binary available for me. Unfortunately, I don't see a parser for Bril to JSON, which is not written in Python. But let's double check. New text decoder. Where is this text decoder? Is located. It didn't make anything clearer. Bril TS. We have a list of stuff, but it's probably Bril TS probably just reads stuff from JSON. That's so sad. What is Bril CK? Okay, it is an interpreter. It is a thing that checks something. And this one converts TypeScript to Bril, probably a subset of TypeScript. I don't want to use ooh. What is oof? Oh, it's one more Python package and project manager. Do we have it? Clicks search. We don't. Blazing fast and all that stuff. Very cool, of course. Oops. This thing uses some grammar definition, probably from this library. Okay. Parse parsing toolkit for Python. Okay, the good news, the lark is packaged. Python JSON. Is it built in library? Lark parser. Probably it should be built in library. Okay, let's try the following trick. Geeks shell. Lark parser. Okay, and now Python Bril txt. Cool. At least it didn't throw any exceptions. Txt was pretty printer. Okay, how to run a particular function from Python. -help. Probably -c. -c Bril to JSON. Bril to JSON. And now we need test enter p core jmp Bril. function. Thank you. Wait, produce always the same result. Oh, okay, because okay, we will come back to it after the break. We have a 15 minutes break, so I can make a few snacks for myself. It's really hard not to get back to work before the break finishes, but I was very successful with waiting until the end of the break before actually starting to work again. We stopped at the moment where we have our environment for Python already, and now we just need to run a function from a particular file to actually produce some results we need. So let's go back to work. Oops. The model is not named anyhow. Parse Bril CS6120. What does it mean? Okay, it means that minus p is present in args in CLI arguments, so it somehow changes the behavior of this function. It always prints this program. What is happening? Python. What the heck? Okay. What is going on? This is really strange. I am like very puzzled. What the heck? Okay. Now it somewhat working. What was happening before, I have no clue. Oops. Okay. Test enter p control p. We somehow managed to make it work. Okay, we have TMP TMP. Actually, we have a working tool for transforming Bril to JSON, and it's a very ugly way that we used to run it. But later, maybe today or tomorrow or some other day, I will package it inside the repo, so we can have a binary, a wrapper in the environment which will call the appropriate command. But for now, let's skip it and go back here. Now we have TMP GMP JSON. Good, how it looks. It's interesting that jump operation have a list of labels as argument. Operation const dist. But okay, let's get back to the video.
If the instructions opcode in, and then we need to figure out what our list of terminators is. I realized in the previous video that I made things sound a little bit too simple. I said that the only two terminators should be jump and branch, but to answer questions like this, you shouldn't listen to me, you should go to the actual documentation for Bril. So let's look at the documentation here. The documentation has a section called the language reference, and the first one is not going to be very helpful for this discussion, but it's going to be super helpful for like understanding the structure of Bril programs, and it tells you what a program is, what a type is, what a function contains, all that stuff, like what fields exist on which objects. But what I really want to know is like what the actual available operations are. And the way that the Bril documentation is organized is that there is a base set of operations and types that make up the kind of the core of the Bril language, and then there are some extensions. So the core just contains integers and booleans and things like adding and multiplying and these kind of very, very basic operations. You can see that there's also an extension for dealing with allocating and freeing and accessing memory, and one for floating point, but we don't need those for now. We just need to look at the operations that are available in the base language. That's all we're processing for now. And of course, all the terminators we're going to have to worry about are going to be control operators. So conveniently, there is a section in here called control that lists all the control operators. And these are the four that exist in the entire Bril language. There are jump and branch, as we saw before. There is also call for function invocation. You can call functions in Bril, which is a very, very useful thing to do. You can also return from functions. Here is a perhaps surprising thing. Generally speaking, in instruction-based IRs, when you call functions, that is not considered a terminator for a basic block, even though it does involve in some way jumping out of the current basic block and executing some other instructions next. The reason is that the call will eventually return to that point in your basic block. So the kind of invariant we want to maintain about basic blocks is that the blocks execute in some way atomically. That is, like, if one instruction executes, then they all execute. And that is still true of when you can have call instructions kind of mixed in the middle, because you will be calling the function, but eventually you'll come back to that basic block and you'll finish the rest of the basic block. So generally speaking, call is not a terminator. However, the one that I left out was ret. That is, if you return from a function, that immediately stops the basic block, that immediately stops the execution of the function, so it should also break up the basic blocks. So I guess the way I'm going to do it is I'm going to have a list at the top called terminators, which is just going to be a tuple of all the opcodes that I want to consider to be terminating instructions. So that has not call, but jump and branch and return. And I will do something if the opcode for an instruction is in that list of terminators, that tuple of terminators. So I'll do something with that. In particular, I need to, as the name implies, terminate the block. But otherwise, I think that we need to terminate the block, and I guess we need to start a new one. So what I'll do that is that I'm going to use Python generators here. So I'll say like yield the current block. That is, let the client see that we have formed a complete basic block, and then I will set cur block to be a new empty fresh list for us to build up. Okay, so I think that's all good for instructions. That is, like, for terminators, we'll add them to the block first, and then we'll yield that completed block that has now has an instruction at the end. So when we hit a label, we will want to end the current basic block. So I think that the easiest way to do this is just to say yield cur block, just as we did before. And for this version, it's going to be super useful to be able to like associate blocks with the labels that they start with. So I think that the way I want to do this is that when we finish a basic block, instead of just saying cur block is the empty list, just like starting a new fresh one, I think I want to say that the next block starts with the label that we just hit. That is, like, we just sort of finished a block, we hit a label. I would like to include the label at the start of the next basic block. And of course, labels aren't like actually part of the code that runs those basic blocks, but it's going to be useful to have those labels sitting around so that we can still jump between blocks. So the way I'm going to do this is to put the instruction in the basic block, in the next basic block we start. The last thing we need to do, which I almost forgot about, which is that we need to emit one last basic block. That is, if we're still forming a basic block and we get to the end of a function and there's not a control operator there, that is, there's no return, there's kind of an implicit return there that we need to consider at the end of the last basic block. So the last thing we need to do is yield cur block. And this at least is a good start. We can debug this in a second, but I will first just say that will print out every block in the program. So this should be pretty simple for the program that we just saw. Hopefully this does something interesting.
Okay, let's try to split all that stuff into blocks. Function. Everything here is valid stuff. What we want, define terminators. It will be list of GMP branch read, right. Now form blocks. It will be instructions to blocks. List first instructions. Let's first do this, and for each function instructions to okay. inconvenient data structures in scheme. Can somebody implement closure data structures in the interface for them, please? Vector. I iterate over instructions. Okay, we need to try to understand how our accumulative value will look like. Unfortunately, we don't have out-of-the-box immutable data structures for dictionaries or something like that. What we can do, instead of trying to come up with a good data structure, we can just have a few small values which we are working on. The problem is that right now we have only one accumulator value where we need to store a few different things, which means that every time we need to serialize it into our accumulator and deserialize, and we don't have a convenient way to access the internals of it and to destructure it. That is why actually we can use match to destructure it, which probably is okay. It's 9 match, and we match our accumulator. Sorry. What we will have here? We will have current block, current block, blocks, what else? Do you have examples? We need to open parentheses, and let's construct a list of blocks X like this. No matching pattern. Bound variable block. Okay. This one works. This is somewhat a bit more convenient than what we had, but the fact that we recreate list every time is not very satisfying, it will be a bit tough. On performance, but we don't care. We have very small programs, so we won't see any noticeable delay in this. Okay, so what we do? If member X or terminators we need to return cons blocks current block. Which is almost right, but before that I would reiterate Okay, it's actually almost what we want, but we can build this new block like this. New block, otherwise we return block blocks, right? Wait, even somewhat working. Oops, my bad. Okay. We need only the second value. How hard to read this stuff. Let's instead of x, we just take only ref x. Oh, how about this one? Oh, this is very strange thing. Okay, it was a wrong code. Current block blocks, new block add operation, if member terminator, cons blocks, new block. Otherwise, new blocks. Sounds reasonable. Okay, I probably messed up. I messed up the arguments order for cons. Now it's const, jmp const, and of course it's the wrong order, because the cons and lists work this way, which is kinda stupid. New block vector set. This is so fucking inconvenient to work with scheme data structures. So horribly bad. I just want to add an element to the vector and I have no clue how to do it. How to add an element. This is complete nonsense. Ultimately stupid. This is so bad. So inefficient. Where the false comes from? It comes from label. Okay, how the label looks. Okay, we finally have our blocks. Our const operation, print operation, return operation, and of course we need to reverse. should be color. Cool. Fucking unreadable. By the way, or member or label. One second. Let's S9 print. Okay, now we have operations. Label operation. Seems okay. Thank you, Arei. We have another small break, and we have 25 minutes of the video left. Even if we watch it a bit faster, I'm not sure if we can finish in time, because I still not finished forming blocks. The note I would like to write. How the unnamed blocks are handled. let's get back to our block extractor. What else I would like to do is to make a mapping from a label to block, but holy moly, how hard it is to work with scheme data structures. It's terrible, terrible, completely terrible. I want just an association between a string and a list of blocks, literal or just numbers. And I would like to use most basic association data structure available in Lisp, called list or association list, which looks like, a basic nested list. And it should be like this. Can one label be related to a few blocks? Probably no. So okay, in this case, when we have a one-to-one mapping from label to one block, it's like really easy, actually really easy. Okay, we can add a label and mapping. And now we have two more things to maintain. Label, if label attacks, then sock ref x label, otherwise it will be false. Okay. Oops. And now, instead of this thing, we will do this thing. Oop. And what else? Okay, and we won't need this stuff anymore. Blocks label, and the original label will be false. Okay, now our blocks have labels at the beginning where it appropriate, and nothing if it's not. Looks good. Actually looks not that bad. For this particular use case, we figured out the relatively straightforward way to construct our final mapping. So now you can see we have a first block which have just association operation or assignment when we set variable v to value 4, and after we jump unconditionally to some variable, and in some variable we have operation print and operation return. Which is hard-coded for now to simplify our implementation, not to deal with like unfinished block. Actually let's get rid of this thing. Instead of this stuff, let's keep instructions. Let's define full result. If null, okay, let's match full result. Blocks, whatever. What happens? Okay, label is important. If null, the block blocks, otherwise you see how hacky it is. Terribly hacky. Now we need no need of cutter. Do we get the same result? Yes, but now we don't have operation yet. Okay, we split everything into blocks.
Looks like maybe it's super helpful, I think, to look at the actual code in to decide whether we have this right. That is to read the human readable text representation. So does it look like there should be 3 blocks? That is the first one that contains the constant and then the jump. The second one that just contains the constant And then finally, the last one that we are going to include the label and then the print statement. Yes, okay, so I think this is right. I think at least for this one, I think we have something that's working. So great, we have our very first version of our basic block formation algorithm. That's not a CFG, it's not a CFG extractor yet, but we do have our basic blocks. Now would be a great time to take it from here and give your best shot at doing the rest of the algorithm. That is like taking this list of blocks and actually implementing the pseudocode that we developed together for forming an entire control flow graph. That is a bit something that represents the graph from blocks to blocks. That is the successor relation. That is like which basic blocks are the destinations of jumps from other basic blocks. So feel free to pause the video and do that now. Give it your best, see how far you can get into it. I'm sure you'll run into some weird, gnarly challenges, and then come back and I'll show you how I arrived at my solution.
What he wants us to do is to go through our blocks and make a graph which takes the last operation of the block, and if it's a jump or branch operation, it adds a couple edges. Actually, we can build those edges easily. But our edges will not be associated with blocks, so we need to number our blocks, or at least name them somehow. But because they are not named for those use cases, for those cases where we don't have labels, of course we need to provide a different name to them. Okay, that means we need to rework this thing. We can name it by the first instruction number. For example, and instead of label we will use this thing, and we will have mapping, and we will have mapping here. No matching patterns. Oh. Okay. Block ID. Один plus block ID. this case. If label attacks, ID we do a cons. How it works: key value a list, key next block ID, value label, label mapping. Very good. Now let's return two values. This is the first one, and the second one will be the mapping. Nice. What the fuck? Take the mapping. It will be force. Okay. Let's just convert it to the list. 2. Whoa, what is happening here? It's all right. This one is unclear. New blocks, block ID, label, mapping, next block ID, label, mapping. If label new block ID, member terminator, new blocks, block ID, label, mapping. Okay, let's do mapping on every step. This is quite empty. Oh, by the way, if label this is definitely wrong. It should be either block ID for the previous block. Okay, looks kinda right. But it should be populated at some point of time when the label. Oh, all right. If label equals block ID, null. Time for a break. Well, I really want to finish it before leaving. It looks right to me. Let's see what What the fuck? Ah, it takes. Okay. Okay, it takes few items. This is why it's okay. If we have a label, as a current operation, let's add association. For the next block ID, and the label. Like this. Okay, now we have association. We can switch them like this from label to block ID. So now we can easily build edges, and having this association and list of edges, we can really build a control flow graph. Oh, let's take a break. Okay, let's now build a graph out of this thing. Instruction to blocks. Now we need to transform blocks to call graph. Okay, now match blocks. We'll take blocks themselves and labels. Now we need to go through each block, take the last operation, check if it's a jump, and add the edge in this case. For this we will need fold, and list of blocks. Match x, we need to extract instructions and ID. That's basically it. pk instr and instructions to blocks to call graph.
So in developing my solution, the first thing that I think we need is, in addition to having this list of blocks, we're going to need a named map of blocks.
I need control flow graph. Control flow graph. That's what I need. Control flow graph. Nope. Something. Okay. Not enough parentheses. No matching pattern. What? Looks right. Also looks right. It can be here. Match blocks ID. This one is strange. Okay, let's try blocks. All looks good. I'm almost sure that something wrong with the order of arguments. Fold, cons, list. First to last. That's what we need. And procedure element. Okay, I see. The order of arguments, but different arguments. And now what? Finally. UX is a mess. PK instruction. Okay, we take last instruction and we print it. Now we need case. I'm not sure if case can work with strings. Key. Maybe an expression which calls should as a for datum. Datum some object. Okay. This sends equal. Oh, that's stupid. Cont. And the funny thing that we can't use match to destructure instruction because match is not that good with lists. So we will do socref instruction and labels. Socref instruction labels. Append accumulator okay. We take accumulator and we do map over labels. If labels what we want to do with labels, we want to find okay, we just put cons id socref mapping x. Nice. Hmm? Whoa, that's interesting. Mapping look correct. Cool. Let's check. That's all we need. Value operation jump to somewhere. Labor. Okay. One more missing thing. If we have labels, we also need to add accumulator will be list and false. Will match accumulator and will do it this way. Edges. And previous one was Okay, we have our graph built, and it seems right. We can jump to the second node from the first one. And from the second one, I mean to the third node. And that's right. But we can't reach this node, never. Which looks reasonable to me. Probably we don't even need reverse. Yeah, we built it in the right order already. Good.
So my first tactic, and this is not the only way to do it, is to write a separate function that you might call the block map function. And this is going to take a list of blocks, a sequence of blocks, and it's going to iterate over them and create names for every block. And it's going to do that with the label that might exist at the top of the block. And if you don't have a label at the top of the block, it's going to invent a name for you. So this way we will have a kind of regular representation that gives us a string way to refer to blocks when we're forming the CFG. So here's how this is going to work for me. I guess I'm going to have this out dictionary that's going to map, again, names to entire blocks, and I'm going to iterate over the blocks and add them to this dictionary. So eventually I'm going to return this out. So I guess there are two cases. I need to do something like out name equals block, but first I need to figure out what the name is for a given block, and there are two cases here. Either we have a label or we don't. So here's how to tell. That is the block 0, that's the first instruction. We're going to see if that has a label key. If so, then the name is just going to be block 0 label. And it occurs to me that we don't need to keep around a label anymore because it's kind of redundant in this representation. That is, so we just need the instructions that format the body of the block. So we can just say that the block is now block 1 to...
Previously, in the previous video, he didn't save label as a part of the block. And now he does. But okay. Saving the label makes sense because this way you can easily understand if some labels attached to the block. The only tricky part here is that if you have multiple labels for one block, going one by one, but it's probably not the case in this language, either in its grammar or just in the use cases, so we can probably ignore such cases.
The end. This is Python syntax for make a new list that is like the old one, except it skips the first element. Okay, so otherwise, then we don't have a label at the beginning. We're not going to do anything to the block. All the instructions are important. However, we do need a name. So we'll just make one up here. So we could say just B1 or whatever. You could just sort of randomly create a number to go at the end here. One random idea that I have is that we could just get a number from the length of the out map so far. So the first one will be B0, and then eventually we will every time we'll add something. This is guaranteed to be unique because we're constantly adding to the out array. Okay, so I think this works. Let's find out together. Very suspenseful. Let's just create this thing called name to block, and that's going to be block map applied to forming blocks here. And we're just going to print out this name to block map. Okay, fingers crossed. So it's a little hard to read, but it looks like we have a block called B0, one called B1, and one called somewhere, which sounds about right. Okay, so I think we have names for all our blocks. The next thing we need to do is actually compute the successors for these blocks. We now have this name to block thing. I think it's going to have to work by iterating over all of the blocks. So the blocks are in the values of the name to block map. So I'll just say for a block in name to block.values. I thought better of it. I'm going to make a function called getCFG, and this thing is going to, I guess I'll write a docstring for myself. Given a name to block map, so this is going to produce a dictionary that maps names of blocks to lists of names of blocks that are successors of the one on the left-hand side. I hope that makes sense. In any case, I'm going to do my loop here, and then call it down here. eventually I'm going to print out that CFG. All right. Okay, so what I'm going to do for each block is find out what its successors are. That is, the thing that I'm producing is, again, this like output dictionary, and then we're going to eventually do like out. I guess I actually want the name here. So now we have the name also of the block that we're processing. In any case, we need somehow to produce a list of successors of this block. Most blocks will only have one successor. Those with branches at the end will have two successors. But in any case, this is what we need to do, and eventually we need to return out. Okay, but we need to compute those successors. Everything that matters about computing the successors we can think of by looking at the last instruction. That is, last instruction might be a jump, or in which case we know exactly what the successor is, or maybe it's a non-control operation, in which case we know that the successor is the next block in the sequence. So I guess I'm just going to do that now. I'm going to take this like last item, that's block -1 in Python syntax. And we're going to do something with this. So I guess there's a few different cases. We can say like if we're going to have to do something if it is a jump. In fact, I think that we can, let's actually take a look at this, at the code. So in the JSON representation, jumps and branches use a key called labels that indicate the labels that they are pointing to. So both the jump instruction and the branch instruction just give us the names of the blocks that are the successor to this block. So I think that these two cases we can probably handle the same way. That is like jump and branch. The successors are just, this is meant to be the last instruction, the last instruction's labels. So I think that's all we need to do. And if that's the case, then those are the successors to this block. I hope I have that right. The other case we have to worry about is the other terminator. So if that last operation is return, then there are no labels that are arguments to the return function. In fact, we can confirm that by looking at the documentation. The return function, it's just a ret. It doesn't have any arguments or anything. If it's a ret, then the successors are nothing. That is, this is an exit block. It doesn't have any out edges coming from it. But we're still not done, because there's a chance that this is a non-terminator instruction. That is, that we have to worry about the case where the block falls through to the next block, and we don't have this convenience of just being able to get the label of the block for the from the instruction that's the terminator. And we have a little bit of a problem, because now we need to ask the question, what is the next block from this block? And so far we've just been maintaining a dictionary, so it's not really a well-posed question to ask what is the next block after this one. So I'm going to take advantage of a little bit of a Python magic to make this easier, which is that Python has a collection class called orderedDict that is guaranteed to maintain its order, which means that when we're building up this block map, we're not just going to be making an unstructured map, we're going to be making one that maintains the order that we inserted in. So we can ask the well-formed question, what is the next block now? If you're doing this in some language that doesn't have this like orderedDict thing, it might actually be cleaner not to. You can just emit an association list that is like just pairs of keys and values instead of using a dictionary. So that means that in this getCFG function, I now have the ability to, and this is not very elegant, I have to admit, to use Python's enumerate utility to look up the index of the current block that we're looking at. So now it's possible to ask, forgot this needs to take an argument, it's possible to ask like name to block.items, let's call it keys actually. So if we get a list of all the keys, I would be the current one, we can get I+1. So the successor to this block will just be I+1. So I know this is going to be a problem if I'm at the last block already, but I'm just going to give it a shot for now, and it is almost certainly going to crash. In fact, maybe I would like to watch it crash when we have to deal with the last block. Yes, it's going to do this. It's going to crash when it hits the last thing, and of course that is out of range. So we can fix this, and again, this is really not terribly elegant, but we can just say there are no successors. It's just like having return if you're at the very end. Otherwise, do what we were going to do anyway. Did this work? No. Maybe, if you want to, you can debug my code by, maybe you've already figured out the bug, but I now need to figure out what I'm doing here. Of course, this should be off by 1. Great, so I think we kind of have a CFG here. That is, like, we named these blocks before. I guess it would be nice to print out. In fact, I'll print it out in a slightly nicer way. So it's easier to read. So we know we have these 3 blocks. They got these 2 invented names, B0 and B1, and then somewhere, the successor of B0 is somewhere because it jumps there. The successor of B1 is somewhere because it falls through. And the successor of somewhere is nothing because it's the end of the function. Woohoo, I think we got a CFG. The next step is just for fun. I'm going to draw these CFGs as actual graphs using the GraphViz tool. If you've never used GraphViz, it's pretty cool. It is just a way to like output a textual representation, get it turned into a nice little like visual graphic. It's not pretty, but it's super, super nice for getting a quick visualization out of compiler tools. So I'm going to do that just using the CFG that is like the successor map function that I just emitted. That's not going to be that hard. Fortunately, the dot format that GraphViz uses is really, really simple. You just have to say like digraph, and then you give it a name, and there's going to be like opening curly braces. Thanks to Python formatting, I got to do that twice. Anyway, I got to say like got to give this graph a name. Anyway, just to sort of show you what that looks like. I don't want to print this stuff anymore. So yeah, so we got this digraph mains. We're going to print all the edges. So we're going to make one vertex per CFG node, per basic block. So we'll just do some indentation and print them and add the name of the block. I guess that's all we need, so we don't even need the stuff. We'll just print the name of the block. Okay, great, cool. Now we will add the edges. The way that this will work is I'll just loop over the name to block map. So we'll get the name and the successors, the name of the current block and some successors, and name to block. And we will, the syntax for doing this is just that you have one name of a previously declared vertex mapped to another name, and you can just put in, I guess we need to loop over the successors. That should do it, and finally we just need a closing curly brace, and I think we should be all good. That's not right at all. Of course, I meant to loop over CFG, not name to block. Hopefully this works. Okay, so we got declarations of the 3 vertices, and I think we also got just 2 edges, B0 somewhere and B1 to somewhere, and I think that's it. So I think that this is a valid GraphViz graph. So we can just pipe that thing into .tpdf. CFG.pdf. I think this works. And we can view this wonderful control flow graph. Of course, the fact that this CFG extractor and graph drawer works on exactly one example should not be satisfying at all. In fact, it should be somewhat suspicious that there are probably issues going on with the rest of the language. That is, we've just done one tiny little example that doesn't even have more than one instruction per basic block most of the time. There are definitely bugs in this, I can tell you that. I sort of skipped over a few cases that will certainly come up when we run this on more realistic programs. So the next thing I want to show you is a convenient way to do testing. It's not required that you use this at all in 6120, but it is what the rest of the Bril infrastructure uses, and I'm going to show you this tool for testing that you might find generally useful when writing small tools as part of a larger compiler. That tool is called Turnt. Turnt is a testing tool, the tiny unified runner and tester that we made a couple of years ago, that is super, super simple. All it does is run a command, like say this command right here, on several different files, and then check that the output matches a pre-computed output on disk. So it doesn't do any it doesn't work like unit tests. You don't have to write the expected write checks for what you expect your function to do. You instead just do this super simple thing, which is to make sure that you match some pre-computed output. This is a really nice way to get most of the benefits of testing. That is, you can make a few changes and then run your program on a whole bunch of inputs to make sure nothing broke while you're doing refactoring, for example, without a lot of the overhead of testing, of traditional unit testing. That is, you don't have to write these complicated specifications. And this I just find in my experience is a super useful way to go about gaining confidence that your implementation for these little compiler tasks actually works. So I'm going to recommend that you explore this. It can be useful just to get familiar with it, even if you don't use it. And I'm going to apply it to our little CFG extractor now. Turnt is also a Python tool. You don't need to do anything fancy to install it. You can just do pip install turnt. I already have it installed. Do I? Apparently not. Okay, now I got it. Great. But in any case, it is the tool that is used in all of the test infrastructure for Bril. So that test directory that you saw before, it has a bunch of inputs. So for example, the interpreter directory has a bunch of tests for the interpreter. It has this, let's see, it's got a divide program. And if you look at that, it's just a normal Bril program, and then checked into the repository is an example, is the output of that. That is what the interpreter should print. And the key to working with Turnt is that there is a config file called turnt.toml, which is just indicates what command we're supposed to run in this. And there's other things that you can read about in the README for Turnt that you can put in the configuration file. But this is the soul of it. You just kind of write down this command to say that I'm going to run, I'm going to convert the input file, that's this one, .bril in this case, to JSON, and then run the interpreter on it. And that's what's going to be captured in the out file. Super, super simple. And if we run Turnt, we can check that this is the case. So I just go over to the interp directory, and if I just say turnt div.bril, this will run those commands and say, okay, you do match exactly what's on the disk. A different thing that you'll find super useful, a combination of flags, is the verbose and print flags, which just say, I'm going to execute this command and just show you the output instead of comparing it to the expected output. So this is a nice way to not have to remember that you have to put the less thans in the special place and the pipes in the special place in order to run the command every time. This is just a way to have a reproducible way to run the same command on a whole bunch of different files. For example, there's another here that, well, that's surprising, but other than that, you can see that this makes it easy to run the same command on multiple files just to observe the output while you're debugging. In any case, we're going to ignore that bug in the interpreter right now. I actually don't know what's going on. I think it's just an old version of the interpreter it's trying to run. And we're going to flip back over to our CFG example and set up some testing infrastructure for it. So it's super simple. All you got to do is have a test directory. You don't even need a directory if you don't want to, but in any case, you can put in a put a file called turnt.toml and start typing your configuration. Again, there's a whole bunch of configuration options you can learn about in the README for Turnt, but the big thing you need to do is just say command and then type some command here. And then I'm going to just scroll up and look at the command that I was running before. I don't want to actually feed it through dot exactly. I just want to run the our extractor to print the graph specification. And instead of hard coding a specific file name here, I will now just say brackets file name. That gets expanded to the file name of the current test. I will also need to change the path to the Python script that I'm running because now I'm under this test directory. These commands run in the directory where the file names are. So like this, where the test files are. So this will just be jump.bril, for example, if we do that, and we'll need a relative path to the script we're actually trying to run. So the next thing we need is a file to actually run this on. I'll just start by copying over an existing test. So from the test directory, the interpreter tests, we had this great test we were using before. I'll copy it here. We can run turnt on this immediately, and will tell us that something is wrong because we don't have an expected output yet. One of the flags of turnt is diff, which will tell you what's the difference between what is on disk and what we're actually outputting. So this diff is indicating that there was nothing on disk, and the and everything is being added. So in order to like mark this as the correct output, it looks like the correct output to me. The last flag to turnt that you want to use all the time is turnt save. This saves something to disk called jump.out. We can look at that. It is exactly the output we expected. And then finally now, if we do turnt jump.bril, this says, okay, that is, you match the correct output. And just to check that we're actually testing something meaningful, if I edit my CFG file and say like, print something totally different, and I say turnt diff jump.bril, I should now get a difference indicating exactly what changed. So as we improve the output or we make changes, it can be super useful to look at the diff to make sure that those are expected changes. And if so, we can do save to update the expected output for future runs. So I suppose to make things a little bit more interesting, I will add a second test, and I'll do that just by copying jump.bril. I guess I'll say, just call this another test. One thing that I would love to test is when we have more than one instruction up here, or another thing I think would be great is to say that we have an explicit return at the end. And let's see what happens. Just to see the output, we can say run another.bril, and unsurprisingly, we have already found a bug. Maybe you can see what the bug is. I'll give you a few seconds to ponder. You got it exactly right. The bug here is that there is no block 0 for one of the blocks. The particular block in question is the one that appears after the ret here. That is, when we were forming basic blocks, we weren't careful enough to check whether there would be any instructions at all between a terminator and the end of the function or the beginning of the next basic block. So it's actually going to be a problem as well if we have a jump right before another label. So we can fix that in our script real quick just by saying we only are ever going to yield full blocks, rather blocks with at least one instruction in. So we can just say if cur block, then yield that, and just do the same thing down here, and hopefully that fixes our problem. Hey, it works. Cool. So this looks like the right graph. We still have the same CFG despite those things that I added. So I'm going to go ahead and save this as the expected output. Now we can run all the tests for the script by just saying turnt star.bril, and it will run both of them and tell them that everything's going okay. I encourage you to, once you have a CFG extractor or anything else working on Bril working, add a few more tests and keep expanding your test set as you identify bugs. Just add a new test that exercises that bug, commit the output to your repository, and build up a larger and larger set of tests. For example, in the main Bril directory at the root of the repository, there's a whole bunch of tests. You can just do make tests to run the entire suite, and you can see that we've just been building these up over time. As we made small tweaks and found bugs, it's really easy to just add one more test, and pretty soon you have dozens and dozens of tests, and you can be reasonably sure that you didn't break your code when you make small changes, because you can easily check a very large number of inputs to make sure that they're still doing the right thing. Good luck, and I hope you enjoy using turnt. And please ask any questions you have at all about the Bril infrastructure. If you're confused about any of the documentation, please post questions on Zoom.
We did everything except the writing a benchmark. This one I consider we covered with this task. Oh, this one. So it's just a matter of couple lines. The rest is done. The only thing I would like to do is to package all the tools so they can be available via Gix shell for future lessons, but probably we will do them some other day. Okay, I think that's it for today. Thank you everyone who joined and hope you enjoyed. Bye bye.